Hello everybody, my name is Chris Brady, author of the Boeing 737 Tech Guide and the Boeing 737 Tech Site. And this is the second of a series of 3 presentations on flight controls. This one's covering Yaw. So I'll be looking here at Rudder Control, Rudder Trim, the Rudder System Enhancement Program, Rudder Power, Yaw Damper, and the Vertical Stabiliser. As always, please treat your company training and their manuals as the authoritative source of information. Okay, starting with the rudder. The rudder's got a maximum physical deflection of 29 degrees left or right of centre. It was only 26 degrees on the classics, but it was increased slightly for the NG as it was envisioned, and in fact it happened that the aircraft were going to be made with a longer fuselage length, the 8 and 900. So the extra rudder deflection was sort of future-proofed in for them. Although that maximum deflection is 26 degrees, the total authority of the rudder is reduced with indicated airspeed due to something called blowdown, and this means that low constant hydraulic pressure is applied to the surface by the actuator. The movement of the panel reduces with speed as the dynamic pressure on it increases. For classics, which are the only generation that I've got data for, but it's very similar to the NG and the Max, I'm sure. The figures for total travel are as given there. So whilst the aircraft's stationary, it's the full 26 degrees. At 150 knots, it reduces to 19 degrees. At 258 degrees, and at VMO 340 knots, it's down to just 4 degrees. Tabs. I've put this in. It's not really a trick. It's more kind of to make the point that unlike the ailerons and elevator, the rudder does not have any either balance or servo tabs, because it is, or at least always should be, always hydraulically powered due to the level of hydraulic redundancy on the rudder system. And for the same reason as that, there is no manual reversion in the sort of cable and direct linkage sense of the word for the rudder. All right, so looking toward the top of the rudder here, let's have a look at the balancers. So the balance on the top is a horn balance, and although there are weights in that, its primary function is aerodynamic, so the shape of that assists with the deflection of the rudder. But the rudder's also got mass balancers forward of the hinge line, and you can see one down near the bottom of the photograph. The weights in the mass balancers are made of tungsten, not depleted uranium. That was something that was used by Boeing. I mean, most notably in the very early 747s, because of its density. That was quickly swapped out for tungsten, which is equally, well, not equally, almost as dense, but without the radioactive side effects. The weights in the mass balance are adjustable for rebalancing, unlike the weights in the horn balance, which are permanently as they are as it comes out of the factory, if you like. The reason why rebalancing may be required, it will be after a repair or a repaint of, well, not only the rudder, but any primary flight control, and that's to prevent flutter or any dynamic instability. Hopefully the reason will just be a repaint rather than damage, but it could be for either. Most of the time, rebalancing isn't required. It depends on the actual paint job, or indeed the nature of the repair on the surface, and the engineers will do a calculation to verify that a rebalancing with weights is not required. And the last thing to say is those little holes visible at the front of the mass balancers, they're just drain holes, just to let the water out. Okay, well, one other thing about mass balancers is on the 737-1 and 200 series, they can actually be used to age the aircraft. The the first 737s off the line had three mass balancers, as you can see in the right-hand photo there. That was until 1970 when they dropped down to two mass balancers, which apparently save 40 pounds in weight. And then in 1988, they managed to eliminate the upper mass balance as well, just leaving one mass balance in the centre of the rudder. That's still the current configuration in all 737s today, right the way through to the MAX. So all the evolution was done in the 1 and 200 series. The reduction in number of mass balances probably because rudders have become lighter as the constructions change from fiberglass to graphite and composite materials. On to rudder control. Now, there's quite a complex photograph there on the right. I'll come back to that in a minute. Let me just sort of explain what we mean by rudder control. So, if you probably all aware, I'm sure the rudder is hydraulically powered by PCUs that are located in the vertical stabiliser in the tail. But the inputs, of course, are from us in the front via the rudder pedals. So that input has to get from the rudder pedals at the nose of the aircraft all the way through the length of the aircraft up the fin to the PCUs. So how is that achieved? Okay, well in true Boeing style, it's done with push rods, cables, quadrants, and other suitable mechanical devices. Okay, so onto the photo. This photo is taken under the flight deck floor, in particular under the FO seat, and the top of the photo is looking forward toward the nose cone. And if I put some labels on it, it might help a little bit, because I agree this is quite a difficult photo to work out, but it was the best I could do. So those two sort of square cross-section rods or linkages, if you like, are coming down from the rudder pedals, which are obviously the other side of the floor. The one on the left is the right pedal, and the one on the left is the right pedal, because of course it's reversed because we're looking up. The two rods going forwards from those pedal linkages, they're actually the brake push rods, because these are from the toe brakes. You know, when you push forward on the rudder pedals, they're the connections that go through to the braking system. I mean, arguably, I could have included that photo in the landing gear video, but anyway, there it is. You've seen it now. So returning to the rudder, these are the push rods for rudder control. They are travelling aft from the left and right rudder pedals, so there's a push rod from each. You can't see the one from the right pedal particularly well, but the left one you can see more of the length of it. Just to show you some other things while we've got the photo up, that silver braided cable that runs almost the full length of the photo, that's the rudder pedal adjustment flex shaft. So when you're adjusting the length of the rudder pedals with that knob just above them, that's where that runs, but from behind that adjustment knob. And the other thing I should mention on there, I guess, is that large cylindrical unit at the bottom of the photograph. That's actually the base, the underside of the first officer's control column. So there you go. That's a kind of overview of what lies beneath the flight deck floor. And I guess the takeaway point from this is that from the left and right pedals, you've got a push rod from each that goes back, and it will meet. They will both meet a quadrant, and on the quadrant is where the start of a cable run occurs, and it's the cables that travel the length of the aircraft, not push rods. So this photo, again, this was actually taken on a Classic, but it's exactly the same on the NG and the Max. This shows a section of the cabin floor taken up, and you can see that there are, well, in this photo there are actually 5 pairs. There are 10 cables visible, and I can tell you, if more sections of the floorboards further outboard were taken up, there would be even more cables. Anyway, the rudder cables, the ones that we're interested in, they're actually the inner 2. I know this because when I was taking the photo, I had my colleague in the flight deck, and I had him moving all the flight controls while I was holding these cables to try and identify which did what. It was actually a longer job than it should have been, but anyway, I promise you, those inner 2 are the rudder pedal cables, and they travel all the way down the fuselage, and then travel back to be behind the aft pressure bulkhead, where they turn upwards into the vertical stab up to the PCUs. Anyway, I have some more photos to show you of this journey. This is the absolute back part of the cabin floor, and at the top of the photograph you can just see the start of the rear pressure bulkhead. So there's nowhere further you can go back on the plane in the cabin than here, and I agree it's difficult to see in the photos, but hopefully you can just about see that there are actually 4 cables visible in this, and the inner 2 again, they're the rudder control cables. So the other side of the bulkhead looks like that, which I think is a great photo. To me, this looks like the bottom end of a Saturn V rocket, but it is sadly only the back of the aft pressure bulkhead on a 737. Now you can see that there are 2 cables travelling vertically up. They're the 2 that we saw in the previous photo. And they're turned upwards by a pair of pulleys. They then go up along the back of the aft pressure bulkhead, and you can see 2 more pulleys which just turn them actually off at about 30 degrees, just to follow the inside route up the vertical stab. And then this is a view of the side of the fin. The forward is looking to the left of the photo. So if I take you through the labelling of these items from left to right, that's probably going to be most logical. So on the left there, you can see I've labelled or identified for you the cables from the rudder pedals. So you can see these are travelling up from behind that aft pressure bulkhead, as we saw in the previous photo. They then turn a corner and travel down toward the centre of the stab, where they meet the aft rudder quadrant. So the forward rudder quadrant was just a couple of foot behind the rudder pedals, and then these cables terminate at the aft rudder quadrant. Now also attached to the other side, the quadrant if you like, are 2 more control rods. These are output rods, and they marry with the or go into the feel and centering unit, which is connected to the torque tube, and the torque tube rotates and gives the inputs via again another pair of 3 control rods to the standby main PCUs. So really, from the feel and centering unit, the torque tube, and the PCUs, it's actually very, very, very similar to the system that I showed you on the previous video with the ailerons. It's unfortunately just not anything like as easy for me to show you the the photos of how it works on, you know, behind the panels with the rudder, because it's so inaccessible. I mean, as you can tell by the quality of this photo, I took this 10-15 years ago from a distance, and it's the best photo I have in my library. But the function of that feel and centering unit and the torque tube and the PCUs, it's just the same as you saw me able to show you in the wheel well for the aileron system. This is the only decent photo I've ever managed to take of the PCU. It's the other side, unfortunately, so it's the less interesting side. If a PCU can never be described as having an interesting or least interesting side, but there you go. So it's the side without the control rod inputs, unfortunately. But what you can see on this side, up at the right of the photo, are the 4 hydraulic lines. So that's your hydraulics A and B flow and return lines, which confirms that this is the main rudder PCU and not the standby rudder PCU, because the standby rudder PCU has just got a standby hydraulic system feed, so it would only have two feed lines, or 1 flow and return. The actual main housing of the PCUs there in the middle, and you can just about see on the left hand side the piston rod which is attached to the rudder, which is just out of shot to the left of the picture. Okay, on to rudder trim. Now, if we go back to the photo I showed you a couple of slides ago, this is probably the best way to visualize it. Now, the rudder trim sends an electrical signal to the rudder trim actuator, so it's not done by cables at all. It's an electrical wire. Now that moves the rudder trim actuator. Again, it's virtually identical to the same rudder trim actuator that you saw in the wheel well, or can see in the wheel well, where you saw it in action on the video I did, where it moves, it biases the feel and centering unit. In doing that is connected to and turns the torque tube, which puts an input in to the rudder PCU. Well, PCUs, which moves the rudder. So that's how that works. Now the other thing is, because the feel and centering unit is also connected by the control rods to the aft rudder quadrant, and in turn the cables, and in turn the rudder pedals, this actually back drives the rudder pedals through the rudder cable system, and that is why when you move the rudder trim knob, the rudder pedals move. It all happens from there. So there we go. I hope that explains it. I say apologies once again that the photos aren't the best, but it's a minor miracle I've managed to accumulate these photos in my career. But there you go. You can see it there. And another word on rudder trim. Again, as I've written, it's perhaps worth remembering that because the rudder trim takes an electrical path to the PCU, if a rudder control cable were to break in flight, and I have to say I don't know of this ever happening. I mean, Boeing might, but I certainly don't know. Rudder control would still be available with rudder trim, so could be worth just keeping that little nugget of information in the memory banks. However, if there's a jam in the cable or pedal system, then rudder trim couldn't be used, because the feel and centering unit would be held in place by the cable and rod system. So this sort of get out of jail free card will only work if a cable is broken. Hopefully you'll never need to use that information, but there it is. It might just help. Now this, for those of you who've not seen it, this I promise you is a photograph from a 737. It's how the rudder trim and aileron trim looked on the 1 and 200 series. They are enormous knobs. They are lifted straight from the 727, and from an era when there was much more hand flying and asymmetric thrust. before the days of autothrottle. And again, I feel I ought to explain that on the 737-1 and 200 there was no autothrottle. Now, in actual fact, there was a retrofit option, but very few 200s ever had it. And of course, asymmetric thrust, even a minor amount can lead to a necessity for trimming. Anyway, winding the clock forward a couple of decades to the 80s, the classics were born, the 3, 4, 500 series, and they originally came off the production line with this blade-shaped knob. In actual fact, it's not a blade. It's supposed to represent the rudder, in keeping with controls looking like the surface they are intended to move. If you think of the gear lever, it's got a wheel on the end. The flap lever's got a sort of flap cross section on the top. The landing lights have got sort of lights marked in there. So that was the logic. Boeing were just being logical by making a rudder shaped knob. But this had to change in 1990 to the present round sort of fluted knob that we know and is still in production with the Max today, following the crash of a US 737-400 which overran at LaGuardia with full left rudder trim set. Now the accident report, if you want, you can just Google that reference there to read it for yourselves. But to summarise it for you, it's on that flight there was a jump seat occupant, deadheading crew member actually, and it is believed that the jump seat occupant inadvertently moved the knob when he placed his foot on the panel there. Now, according to the report, the jump seat occupant denies doing this, and it was noted that the FO put something down on the aft electronic panel, and the FO denies doing that. So we don't know exactly who did it or even why, or frankly we don't even care, because the purpose of accident reports isn't to apportion blame, it's to prevent reoccurrence. All we learn from it is that somebody somewhere somehow moved, I'm sure inadvertently, the rudder trim knob, and it was easy to do so because it was of such a shape that it could be easily caught and moved, and B, at the time there was no guardrail going around the aft electronics panel. So the FAA issued that AD reference up at the top there to mandate that the rudder knob changed to a round shape, and that the guardrail that I've highlighted in the lower photo be fitted to all 737s, and those two actions have, as far as we know, prevented any similar reoccurrence. Now, that's not to say there haven't been rudder trim runaways since, and I know because I've had one. Now, page 29 of the report that I referenced on the previous slide states that many pilots reported rudder trim knobs sticking out of neutral after unintentional activation. A knob with debris underneath or a mechanical abnormality found later on some aircraft can keep driving trim after release, in spite of it being spring loaded to the neutral position. And this is exactly what happened to me back in 2006. I was about to take an aircraft up on a maintenance check flight after it had been in heavy maintenance for a month or so. It was also a customer demonstration flight for end of lease as the aircraft was being handed back. Now, fortunately, before I do these flights, I do quite an extended lot of pre-flight checks and of course in-flight checks. But as part of those pre-flight checks, I always exercise to the full extent all of the trim. You know, rudder, aileron, stab trim. Now, when I was safely on the ground, thank goodness, I got to the point in my checks where I moved the rudder trim. It, instead of spring loading back to the neutral position after I released it, it stuck in the full travel position, full left. And it just drove the rudder trim all the way to the full extent, which horrified me. I moved it back to centre and tried it again in the other direction, and the same thing happened. The rudder trim went full travel in the opposite direction. Now, bearing in mind the flight I was about to do involved a couple of engine shutdowns and relights, I would have had to have been using a lot of rudder trim on that flight. So thank heavens I did this check. But anyway, enough of the war stories. What actually happened? So you see, I've highlighted in the circle this handheld PA microphone. This was a modification that the airline concerned had done to install this on the aircraft. Now, the aircraft was on a 7-year lease, and at the end of the lease, when you return the aircraft, you have to demodify any mods you've done that the leasing company don't want, and this was one that they didn't want. So this had to be taken out. Now, this was held onto that stand by a bracket, which was held in place with 2 screws, and the 2 screws fitted there. Now, full disclosure, the top photo, the first photo, was not actually the incident aircraft, but the next photos I'm about to show you are all from that aircraft that I had this event with. So those are the 2 screw holes there, and I just point out to you that they are on a perfect line with that rudder trim knob. Now, when the rudder trim unit was taken out in the subsequent investigation, this is what was found. The 2 screws that had been used to hold the bracket that hold the microphone in place had been taken out, the bracket removed, and the nuts and bolts, the 2 nuts and bolts, had been replaced. Because they'd been replaced and the bracket hadn't been replaced, they were a fraction longer than they had been before, about 1/4 to 1/2 centimetre, I believe. And this is the result. That there is the unit which is come out of that bottom photo, and you can see that there is a large bolt-shaped dent on the rudder trim housing. So what had happened is that the bolt had pushed that forward in its housing. It had pivoted around the light plate at the top, which was pushing the knob backwards. And because the knob, as you can see, has got a fairly wide sort of brim to the bottom of it, it was binding on the panel itself. So when you moved it, it was stiff to move, and it stuck where it was held. As a result, the thing wouldn't spring back, and it would just stay where it was put, and you would have had a very, very, very difficult job in trying to centre the rudder trim after that. So anyway, I guess the moral of the story is do your checks thoroughly, and anybody involved in modifying aircraft or demodifying them, have a careful think about the unintended consequences of the actions. Okay, on to more regular stuff. The rudder trim limits. Now, I've written what you'll sometimes find is that, but in my experience, what you'll almost always find is that a particular aircraft requires an adjustment of the rudder trim in the climb or the descent. Now, there are 2 reasons for this. The first is that an out of trim condition arises due to the different thermal expansion rates in the components as the aircraft cools in the climb and heats up during the descent. That this is undeniably at least partially true. The the second reason, and I don't know, how much it's one and how much it's the other, but the second reason is that whatever slight outer condition there may be on the ground, it will be magnified at a higher indicated airspeed. As the v squared laws kick in. And this, of course, changes during the airspeed, of course, changes during the climb and descent. Either way, whatever the reason, the acceptable limits of rudder and aileron trim are as I've given on that table up there, and that's a figure which is available to the engineers. So if you find that an aircraft requires more change of trim than given in that table, it's probably worth flagging up to the engineers so they can do rectification work on the aircraft, because there could be something more amiss. All right, last horror story about rudder trim, and this event didn't happen to me, but it was quite famous at the time. In 2011, a 737-700 belonging to a Japanese airline entered a roll that reached 131.7 degrees when, according to the report, during the flight the FO erroneously operated the rudder trim control while having an intention of operating the switch for the door lock control in order to let the captain re-enter the cockpit. And again, I've given the reference for the incident reports there, which you can Google and read at your leisure. They go on to say that it's somewhat likely that the similarities between the switches for the door lock control and the rudder trim control in their operability contributed to the delay in his recognition of the erroneous operation. Now, the two photos you see there show, because obviously it's easy for us to sit here and throw bricks at the poor bloke that did this, but hopefully we're all a bit more enlightened these days, and we'll look through this to the human factors angle of why he did what he did. And I think this photo really speaks volumes for it. So the photo on the left is the aircraft that had the incident, and the photo on the right is the aircraft that the same FO that made the error flew on his previous duty. And you can see that the location of the rudder trim switches is almost reversed with the door lock selector. Now you may ask, why didn't he just look around? But if you think about it, when one of the major times that we use the rudder trim is perhaps in the sim with the engine out case. So we do that by reaching back and operating the rudder trim without looking, because we got our hands full of aircraft, and we're probably trying to focus on the V2. Now, although he wasn't intending to operate the rudder trim, he was intending to door lock selector, maybe there was a bit of motor memory in there. It's a rotary action of a switch of a similar size. I don't know. The psychologist will analyse this more than me, but certainly nobody goes to work with the intention of making a mistake like that. And I certainly always believe that if somebody's made that kind of mistake, it's entirely possible that I could as well. So I pass on this message and this warning for you guys out there. Now, hopefully the problem's been, if not eliminated, reduced considerably by the reference I've given on the bottom, which is the FAA SAIB, which recommended that the operators keep the rudder trim switches in the same position, and avoid a configuration like that 737-700, the photo on the left, which did not help the confusion and the error on the day. So that's what the SAIB is driving at, is basically keep things in a standard place, which of course we as pilots have known for almost 100 years, and which is why the flight instruments are always kept in the same, the basic 6 are always kept in the same sequence on pretty much every aircraft you jump in and out of to make things easy for us. Okay, again, I digress. On with the program. So let's have a look at the RSEP, the Rudder Systems Enhancement Program. This was huge news when it happened. This really was a series of events which almost led to the grounding of the 737, and really was the, if you like, the classics version of MCAS. There was just as much controversy and angst about it. Anyway, let me carry on. So from January 2003, all 737s were delivered with the RSEP installed, and by now all 737s should have had this modification. We can recognise it in the flight deck by checking that the flight controls panel has got a standby rudder on light. That's the giveaway, as I've indicated on the right hand photo. Now, when this illuminates, it's telling us that the standby rudder PCU is pressurized. Now, it may be pressurized either automatically or manually through use of the flight control switches. And I'll come on to these criteria more in a moment. But let's look at the background to this. Why was this change made? And as I say, this really was the sort of MCAS of its time. So 2 737s suffered fatal accidents with huge loss of life during their approaches. In March 1991, United 585, a 737-200 at Colorado Springs, and in September 94, USF 427, a 300 at Pittsburgh. Also in 1996, there was a significant, albeit brief, yaw roll upset to an east wind 737-200 whilst approaching Richmond. Now, the reports are out there on the internet for you to read and digest if you wish to. I will probably at some point in the not too distant future dedicate a whole video to this story, because it is quite a useful one to be familiar with. But over the next couple of slides, I'm going to give you the kind of executive summary of it all. And if I can condense into 3 brief sentences some of the opposing parties, it goes like this. The NTSB said that a rudder reversal scenario will match all 3 events. Boeing, of course, took a different view, and they said that there is no physical evidence that supports rudder reversal scenarios in the 3 incidents. Which actually they're correct, because the physical evidence kind of disappeared, or at least was elusive. The FAA kind of stood in the middle of all this as the arbiter and the lawmaker, and said that no one will ever know the cause with any certainty, so we're focused on making the plane safer. So good for them. So what did they do? It all really hinged around the main rudder PCU that was in service at the time. So pre-RSEP, the main rudder PCU was a single rod. It was quite a complicated single rod, and this is the breakdown of it, the exploded view of it on the right hand side. So it was comprised of a primary and secondary slide that themselves slid within a housing, and these summed the inputs from the rudder pedals and the yaw damper. The NTSB stated that their findings were consistent with a rudder reversal most likely caused by a jam of the main rudder PCU servo valve secondary slide, that's the middle one of the 3, to the servo slide housing when it was offset from its neutral position and over travel of the primary slide. So the whole thing completely malfunctioned. and it led to a rudder reversal, which must have been incredibly difficult for the crew to deal with. Well, I say that, but of course 2 aircraft were lost. So what was done about it? This is the current rudder and PCU arrangement in the graphic on the right, and I've just labelled in grey you've got the main PCU as the lower one, and the standby PCU, the upper one. The torque tube is visible on the left hand side, and the torque tube is where the inputs come in from the aft rudder quadrant cables. Rods. Now, the dual concentric servo valve, the old one on the previous side that was very complicated, that was replaced by independent input valves with separate input rods. One for hydraulic system A, which is the upper one shown in blue, and the other for hydraulic system B, which is the lower one, which I've shown there in yellow. So those rods were the concentric rod arrangement was swapped out for independent rods. Not only that, all 3 input rods, so even the standby input rod, which was never affected, now have individual jam override devices, which are those units attached to the input shaft, that allow the rudder pedal inputs to be transferred to the remaining 3 rods if a jam occurs. Now, these are spring-loaded roller and cam devices mounted to the torque tube, and they've got a breakout load of 18 pounds at the rudder pedals, so it's actually quite a low breakout load. When you think that the aileron breakout loads are around about 90 pounds, so this is quite low, and it needs to be low because the rudder is so powerful. Additionally, a component called a force fight monitor was added to the main rudder PCU, and this detects an opposing pressure, a force fight between the A and B actuators. So it doesn't, just to be clear, it doesn't detect a difference in pressure. So if I don't know, say system A is giving 2000 psi and system B is giving 3000 psi, it doesn't detect that. What it detects is an opposing pressure if one's forcing against the other one, as might happen in a potential rudder reversal or any other hydraulic system input rod or control valve jam or failure, any other scenario, no matter how unlikely. If there's an opposing pressure detected, the force fight monitor, detected for more than 5 seconds, that the force fight monitor will automatically kill the hydraulic powers on A and B and open the standby rudder shut-off valve and energize the standby rudder PCU, and that will bring on the standby rudder on light. So it's protecting against this sort of unlikely scenario. Furthermore, they were installed, and I'm just going to cover the originals and classics in this slide. I'll come on to the NG and the Max, which has got a slightly different system. Not very different, but just slightly. As part of the RSEP program, there was a rudder pressure reducer and a rudder pressure limiter fitted to reduce the hydraulic pressures, drop them down by, well, as you can see, about to 1000 psi on the A side and 2200 on the B side, above 1000 feet AGL. The reason that this was done above 1000 feet AGL, not below it, was for the engine out case, where the engine failure after takeoff, you would want full rudder pressure available. So it's a balance of risk is why this 1,000-foot AGL was put in. Anywho, the combined rudder deflection, the reduced rudder deflection was to permit more effective aileron, well, I've said aileron, but aileron spoiler control in countering rudder inputs. So what they're saying is that by reducing the hydraulic pressure, the rudder won't be able to deflect as much. So you're more likely to be able to overpower it with aileron and spoiler with that reduced rudder pressure, and that will give more time to recover from a full rudder input, regardless of the cause. Hydraulic pressures are restored when the aircraft descends back down through 700 feet AGL, or if the hydraulic system depressurizes, or whenever there's an M1 difference between the left and right engine of more than 45%. So again, this is covering for the engine out scenario, or following a loss of electrical power. So the takeaways on this are that for the classics, the rudder deflections reduced above 1,000 feet. Now on the NG and the Max, I'll come back to the photo in a moment. The difference really is that, well, it's got a different name. It's called the Rudder Authority Limiter. The function is pretty similar. The numbers are slightly different, but on the NG and the Max, it's a function of airspeed, not altitude. It's airspeed. So when the airspeed is above 137 knots, and it does depend on series. I think it's 136 on the 700 series, and it's likely to be probably more on the Max 10. It reduces the rudder output force by 25%, which reduces the rudder authority, and this trips back to normal below 132 knots. Again, or if a difference in engine speed is detected. Okay, so onto the photos. I was sort of struggling to find a relevant photo of the rudder authority limiter, because there's nothing to look at. It's just a valve, So what I've shown here, the upper photo is from a classic that's been retrofitted with the RSEP, as most classics were. And the lower photo is of an NG where the RSEP was installed at build, again, as most of them were. So the differences are that, well, the similarity is that the force fight monitor is labelled up exactly the same. The load limiter is labelled as a rudder load limiter on the classics, but it's labelled as a rudder authority limiter on the NG. Okay, who cares? But the other thing is, because it's a retrofit, that you can see those circuit breakers are being added in after build. So the labelling for the circuit breakers is actually a sticker, a decal on there. Whereas you can clearly see that on the NG photo I've used, they were put in at build, because there's no sticker. That's the way that aircraft rolled out of the factory. Anyway, I mean, that's on the point of pub quiz trivia is that, but there you go. It's of interest, and next time you get on your aircraft, you can look back and find those. I guess the only other oddity that I noticed was that on the classics they've located these circuit breakers in the hydraulic section, whereas on the NGs they're actually located in the flight control section. I go figure why that difference is, but there you go. All right, on to Rudder Power. So obviously we've already mentioned this earlier, but let's cover it properly. So the rudder is normally controlled by the main rudder PCU, which is powered by hydraulic system A and or B. We know this. That's in the FCOMs. Under certain conditions, the rudder is moved by a standby rudder PCU, which is powered from the standby hydraulic system. Again, this should be nothing new. There is no direct cable linkage, manual reversion mode, for the rudder The manual reversion mode, if you want to call it that, is the standby rudder PCU and the standby hydraulic system. There is no cable linkage directly connecting the rudder with the rudder pedals, unlike the ailerons and the elevators. Right, now looking at manual standby control, the way you do that is here on the flight controls panel, and you simply move either a flight control switch to the standby rudder. If in flight you were to notice that the flight controls A low pressure light illuminated, obviously you consult the QRH and it would direct you to move the flight control switch up to standby rudder. And the same for B. If both come on, or indeed you've got a loss of A and B hydraulics, then you'd move them both to standby rudder. The standby rudder will also activate automatically through either the auto standby system, which I'll cover on the next slide, or the main rudder PCU force fight monitor, which we've already mentioned. Again, just to tidy this up, the standby rudder on light will illuminate whenever the standby rudder has been activated, regardless of how it was activated. So that standby rudder on light is always telling you the same thing, that the standby rudder is on. Easy. So for auto standby operation, and those of you that saw the hydraulics video I did, you should recognize this slide. The rudder will operate from standby hydraulic PCU automatically if either flight control A or B switches are in the normal position, the alternate flap arm switch is off, which again is normal position, trailing edge flaps are not up, i.e. you've got some flap down, your aircraft's in the air more than 60 knots, well hopefully those two will be the case, and you've got a low A or B flight control pressure, or the other one is that the FFM's tripped. And if that happens, it'll activate the standby pump, open the standby rudder shutoff valve, and allow the standby system to fire the rudder and thrust reversers. The standby rudder on light will illuminate, as previously stated. Again, to summarise this, if you're airborne and you've got a loss of A or B with the flaps extended or the FFM activates, standby rudder will come on. That's the takeaway point. That's all you need to know. Alright, onto the yaw damper. For those of you that don't know what Dutch roll is, there's a graphic there showing one complete sinusoid or oscillation of a Dutch roll. Now, the 737, one of its really nice aerodynamic features is that it's actually positively damped in combined lateral directional oscillations. In other words, if you set up a Dutch roll or encounter turbulence, the aircraft will naturally stop oscillating. And I know I've done this on test flights, where under controlled conditions I've put in a gentle rudder doublet to test the function of the yaw damper. Now what we do is with the yaw damper off, we put in a rudder doublet and then switch the yaw damper on and see how many oscillations it takes to eliminate that Dutch roll, and it goes within about 1.5 with the yaw damper. It's sorted out almost immediately. And for the sake of interest, I have done this without the yaw damper, or I've delayed putting the yaw damper on to see what the aircraft, to get a bench line figure to see how naturally stable the aircraft is. And I have to say that when I put the same rudder doublet in, the aircraft had smoothed it out in about 6 cycles, which is really impressive. So anyway, the yaw damper isn't required for dispatch because the aircraft's so well behaved and so well designed, and you can verify that in the MEL. However, it is fitted for passenger comfort as much as anything else, because it dampens any oscillations much faster. It's all very well us saying, "Oh, that's nice. It'll dampen within 6 cycles," but if the passengers back in row 22 are starting to feel sick by then that's not good for business. So that we have the yaw damper for that. The authority of the yaw damper is considerably less than maximum deflection of the rudder and the rudder trim. And this seemed as good a place as any to put this graphic in for you, which I borrowed from an NTSB report. So it's actually the graphic's applicable for a classics, but the NG and the max I've given the figures in the text over on the left. Your maximum rudder deflection, as we've already said, is 29 degrees on the NG max, 26 degrees on the classic. The rudder trim limit's 18 degrees, and the yaw damper, it's 2 degrees flaps up and 3 degrees flaps not up. So so you can see the diminishing authority with each control. The yaw dampers, they give input into the main or the standby rudder PCUs. And again, just at the risk of stating the obvious, for those guys who may be new on type or not familiar with the 737, just converting onto it, yaw damper inputs are not fed back into the rudder pedals. Okay, this is because the inputs go straight directly into the PCUs. During normal operation, SMID 1, so obviously we're talking about the NG and the max here, SMID 1 controls the rudder through the main rudder PCU. Now I've used the phrase manual reversion because I think that's how the FCOMs refer to this, but again, don't confuse manual reversion with raw cable control of the rudder. By manual reversion, what we mean here is using the standby hydraulic system. So during manual reversion, SMID 2 controls the rudder through the standby rudder PCU. Note that for primary yaw damping, both SMIDs must be operational, and that's because SMID 1 compares the calculations it does for yaw damping with SMID 2 before it commands rudder movement. So there's a common sense check there, which is great to see because obviously the 737 can sometimes get a bit of a hard press on comparators and things. Like I say, MCAS didn't do it any favours in that regard, but at least the SMIDs talk to each other and get a common sense check before putting any rudder inputs in. So what I've got over there is I've just drawn up a little block diagram schematic for you. So if I take you through that first, that'll probably cover all of the text I've got written on the left. So the yaw damper switch will switch on the yaw damper function of both SMID 1 and SMID 2. And I've drawn that arrow double-headed because if there's a fault or a problem in either SMID 1 or SMID 2, whichever one's the active one at the time, because obviously only one is active at any one time, because one's for normal operation and two's for manual reversion, they will trip off the yaw damper switch because that's only a solenoid held switch, unlike most of the others on the overhead panel, which, as you know, are mechanical and the system can't switch them off for us. And it will also bring on the yaw damper light to alert us that that's happened. So SMID 1 powers the main yaw damper, which through hydraulic system B powers the main rudder PCU, which through A or B powers the rudder. SMID 2 also talks to SMID 1, as we said on the previous slide, for the common sense check, and that drives the standby yaw damper using standby hydraulics to the standby rudder PCU to the rudder. The SMIDs get their information from a variety of sources. They get it from the ADIUs, they get gross weight information from the FMCs. SMID 1 pulls alpha info from the left vane and SMID 2 from the right vane, and they get flat position for max deflection logic from the limit switch on the flap limiter. So I think that covers it. Oh yeah, the Yaw Damper indicator is only will ever show activity from SMID 1, from the main Yaw Damper. The standby Yaw Damper, even if it's in use, will never register on the Yaw Damper indicator. Right, the wittress, which is perhaps little understood amongst the NG and maybe the Max community. This is the wheel-to-rudder interconnect system, and what this does is it moves the rudder during turns in, again I'm using this phrase, manual reversion. In other words, when the rudder is being powered by the standby hydraulic system, in response to control wheel inputs. So, and again, I've many hours of doing this for real in the real aircraft. It does feel different, an NG from a classic in manual reversion in roll. I'm not going to say better. It just feels different. But what happens is when you move the captain's control wheel in manual reversion, it knows you want to roll and presumes that you want to turn. So the wittress kind of talks to the SMID, or the wittress function within the SMID gives you a little bit of rudder to assist that turn. The wittress is only active below 0.4, and the gain schedule changes from 0.3, where it's at full gain, dying down to 0.4. So it dies out between 0.3 and 0.4. The limits for wittress and standby yaw damping are 2 degrees flaps up and 2.5 degrees flaps not up. So just slightly less flaps not up than the main yaw damper. All right. Word on the yaw damper indicator. Those of you flying shiny new aircraft will have difficulty locating this because it's been withdrawn. It started to disappear from April 2010, and not only was it withdrawn from all new build aircraft after that date, but there is a facility for operators to remove it from older aircraft. Although why they'd want to do that, I'm not quite sure. I guess they'd probably do it if one failed, rather than pay to replace it. They would just blank it off, or remove it and blank off the whole. Anyway, a lot of questions were asked by the pilot community at the time as to why and where's my yaw damper gone, or my yaw damper indicator gone, because those of us who've flown the earlier generations, the originals and the classics, we're used to checking the yaw damper indicator in turns as we taxi out. It's part of the serviceability checks. Part of what you do when you taxi out, and of course you see it moving gently away in flight in a turn, which gives you a confidence check that it's working. Anyway, here's Boeing's reason as to why they removed it. So the story is that pre-NGs, so your originals and your classics, they've got analog yaw dampers, or yaw damper couplers, as to give them their full title. And these require crew to periodically check the indicator to verify that it's working, which, like I say, is what we do, most notably during taxi out. The NG and the Max have got digital yaw dampers within the SMIDs, and these are self-monitoring. So if they malfunction or stop working, they trip off, the yaw damper light illuminates, and that alerts the crew that that there's a malfunction, and they've tripped off. Boeing have said, or rightly I suppose, analysed that there are no formal, normal, or non-normal procedures that require the use of the yaw damper indicator. Again, we're only referring to the NG and the Max here. The classics, you do still have to check it works. And they go on to say that the yaw damper indicator was never needed on the NG, and it was only retained on the flight deck for commonality with earlier generations. Anyway, they obviously had a change of heart and decided to pull it back in 2010. So that's the story behind that. We don't need it. It's more there as I guess a comfort blanket to those of us that used to fly the earlier generations. The aircraft or the SMID will self-monitor it much more accurately, efficiently, and quickly than the pilots will, and will switch it off if it malfunctions. So there we go. On the originals, they also had 2 yaw dampers, but they were actually 2 yaw dampers on the main PCU. It was a dual, what's known as a dual yaw damper system, unlike what we have on the NG, which is one on the main PCU and one on the standby PCU. This is 2 yaw dampers on the main PCU, and it was designed that way because of the experience of the 707 and 727. It was expected that the 737 wouldn't be so naturally positively yaw damped as it is. I guess they forgot that the 737 was nothing like a swept wing as the 70 and the 72, particularly the 72, because of course the Dutch roll is more of a feature of the swept wing jet. Anyway, so 2 were fitted to allow dispatch in case 1 failed, because these were anticipated to be MEL items, as in no-go items. If they failed, you needed 1, so they built the aircraft with 2. However, they quickly also found that the second yaw damper wasn't needed. The aircraft was very benign in Dutch roll, and the second yaw damper was dropped when the classics were introduced. The originals have got a yaw damper test switch to the right of the indicator. That's what that little left-right button is to blip. But note that for aircraft with the RSEP installed, the yaw damper test switch is in up, and that's because the yaw dampers were replaced. The analog ones were replaced with digital ones for the RSEP upgrade program on all generations. So the test didn't work on analog aircraft. Okay, on to the vertical stab, or the fin, as some folk call it. Pleasing shot there of one in the evening twilight. So let's start with the construction of it. So this photo is of a fin or a vertical stab stripped back at the factory in Renton. The area 26.44 square meters for those that are interested. Perhaps of more interest is what it's made of. Explain those color changes then. So this is it. Everything you see in grey is glass fibre reinforced plastic GFRP honeycomb sandwich, and there's quite a bit of it, not only on the fin but on other parts of the aircraft as well. Long gone are the days when aircraft were all made of aluminium. The green areas, they're all aluminium or aluminium alloy, and actually the yellow areas as well. The rudder, which of course we can't see what colour it is because it's pre-painted, and the reason why it's pre-painted is so that it can be balanced. Remember me talking about rudder balance earlier on in this presentation. It's a devil of a job to do. There's a whole manual on balancing a rudder, and the maths in it is extraordinary. So Boeing, is a huge favour to operators, paint the rudder before they install it on the aircraft, so the balancing can be done accurately at the factory. Anyway, the rudder's made of a mixture of carbon fibre, CFRP, and glass fibre, GFRP, honeycomb sandwich. As I've already said, yeah, the rudder's pre-painted before assembly for ease of balancing, and that other oddity on the leading edge there, that's where the HF antenna lies, behind that composite area there. And I'll come on to mention the HF antenna in a moment, in a few slides. The fin is or can be prone to icing at certain localized spots after long cold soaked flights, and this pattern you'll see it's quite a familiar one, and the reason for that is that behind those points are the spars, the front and rear vertical stab spars. So obviously they have got more material behind them. It's not just the skin behind the panels at those points, and they absorb more cold over the hours of flight, and they can frost up when exposed to moisture. The other place you can get frost is on the fillet panels, and slightly down there below the stab as well. Again, this is not unusual. Perhaps a little more unusual than the previous frost picture, but it's it's there. Right, this is a photo I took when I asked to see one of the next aircraft I'd be taking on a check flight, and the engineers took me out, and that's the sight I saw. Obviously, it was a couple of weeks away from the flight I was going to do, but it did give me quite a surprise, because that was the first time I'd ever seen a 737 without its vertical stab, and it really made me think, be even more careful than I already am before doing the rudder damper check and putting a rudder doublet into the rudder pedals. And the next series of photos, I think, will have a similar effect on you as well. This is let me sort of orientate you. What we're doing is, in this photo, we're looking at the base of where the vertical stab should be, and we're looking toward the back of the aircraft. So the stab fillet is here on the left, and where I've put those three circles, and there would be four, but you can't see the fourth one because it's hidden by the fillet, are the place where the 6 bolts go that hold the vertical stab in place. That's it. That's where it's held. That's all that holds it on. And you may recall, although it wasn't to a 737, it was to an A300. American Airlines, as I recall, just a month or so after 9/11, an American A300 was lost in New York shortly after departure, when it's believed that the crew were a bit heavy on the rudder following, I think it was a wake encounter from memory, and they overstressed the stab due to rudder input, and it snapped off, and they lost directional control of the aircraft. So this is probably a picture worth bearing in mind before you're too heavy with the rudder in flight. I should say, I mean, I don't want to be overly dramatic about this. The rudder deflection is tested to, I think from memory, 1.5 times the stresses that we put it under on the normal flight, in the normal flight envelope. So there is quite a margin there, but of course it can be overstressed, as the crew of the American A300 found. This is just another view of the exact same thing, just showing the bolts from a different direction. So just to kind of put it all in context. And that's a vertical stab, just sat there on the ground on the hangar floor, minus the fillet, of course, at the front of it. Again, I just throw these in. I mean, there's no great technical insight here. These are photos that or sites that we as pilots very rarely get to see, and I found them of interest, and I pass them on to you. Hopefully you find them of interest as well. So we've mentioned the fillet many times. Let's kind of just address it. The fillet, it's that small bit in front of the vertical stabilizer, that small triangular bit of sort of streamlining. Now I've marked on the photo a gap there between the fillet and the stab. You're not supposed to be able to see right through it and see daylight on the other side like you could on this, but again, this was a photo I was about to take up on a check flight, so the walk around was quite thorough. I drew this to the attention of the engineers, and they assured me it was fine, and they'd get it filled when I landed. Anyway, fortunately, I'd seen the construction of it, and I was quite happy with what I saw. So let me read you the text about fillets and what they are and what they can do. Now this is from these are not my words. This is pulled verbatim from a NASA website. It says the vertical stabilizer often employs a small fillet or dorsal fin at its forward base, which helps to increase the stall angle of the vertical surface thanks to vortex lift, and to prevent a phenomenon called rudder lock or rudder reversal. Rudder lock occurs when the force on a deflected rudder in a steady side slip suddenly reverses as the vertical stab stalls. This may leave the rudder stuck at full deflection with the pilot unable to recenter it. Well, that to me sounds pretty horrifying. Now, I'm not saying that that's why Boeing put the fillet on the 737, because if they didn't, these things would happen. I very, very, very much doubt that's the case. I think NASA could be referring to much more high performance aircraft than a 737, fighter jet or what have you. However, that fillet, what it does do, if it does nothing else, it reduces interference drag and I guess form drag as well from the front face of the stab. Well, certainly the interference drag. If you as you probably well know from your ATPL aerodynamics, any sharp corners on an aircraft exposed to the airflow will produce drag, interference drag. So if you can blend them out as much as possible, streamline them, then so much the better. And in fact, a good recent example of this was on the Max, on the horizontal stab, where the horizontal stab butts up to the fuselage. They've extended the fillet on there for exactly this reason, to reduce drag. But if you see my max differences video for that, and there's a photograph of that as well. This is just a photo that I thought I would throw in while we're talking about the fin and the vertical stab. More times than I care to remember, an FO has come in to me after he's done the walk around and said, "Can you have a look at this? I think we've had a bird strike." And I've gone out onto the forward steps and had a look, and I said, "There, look, you can see it on the leading edge of the fin." At which point, because I always fly with a camera, I've usually got my camera and taken a photo like this and zoomed it in and said that what you're seeing there is paint peeling off the leading edge, and it always happens there, never anywhere else, always there, and that's because that bit is actually painted. The rest of it is just its natural aluminium colour, and as we know from several slides back, the reason why that is painted is because it isn't aluminium, it's the glass fibre reinforced plastic where the HF antenna sits. Anyway, I'm obviously always very, very, very thankful to anybody, an FO, a member of ground staff, or even cabin crew, anybody that points out anything on my aircraft that they're not concerned about. I want to hear about it, and then I can investigate it. And to that end, if any member of ground crew tells you this, and you're in the aircraft, even if the passengers are on, even if the doors are closed, you're kind of duty bound to go and have a look. But anyway, I'm straying way off topic here. And the bottom line is, if there's any doubt at all, if you're not happy with that, you think it really is a hole, you don't have a zoom lens on you, call an engineer. I always say, if there's any doubt, there's no doubt. And if you see something you don't like, call an engineer. They're far more knowledgeable in these things than any of us, and they will tell you, yeah, that's good, or no, we better get that looked at. That's it. That's all I know about the yaw systems on the 737. As always, if you've enjoyed the video, please give it a like, subscribe to my channel, and share it amongst your colleagues. Tell your friends. If you found it useful, they could too. And the more knowledge we all have, the safer we'll be. So once again, thanks for your attention, and I'll hope to have a new video for you very soon.